I have effectively been open circuit design for about 25 years. And this is going to be a talk about software that is meant to do end-to-end going toward a foundry process, a real hardware chip, something that you get back and hold in your hand, that not FPGA, but ASIC design. I'll show a little bit about recent development, near future development. I guess I'll spend, since most of these people here are FPGA oriented, I'll give a little talk about what it actually is before going into development and near and future development. So what is open circuit design? It's dedicated to the development and availability of open source software for ASIC design. So not specifically FPGAs, but real hardware done on real foundries. I've been doing this since I was at Stanford in about 1991 or so. And so these are the components. You'll recognize a lot of them from that era. I describe myself sometimes as treating software like some people like to collect and restore old cars. I like to collect and restore old software. The nice thing about software is you can often just bring it up to speed completely if you know how to do it, but a lot of it is really old code, a lot of it's badly written. It takes a lot of effort. But here are the components. Magic down here, that was one that was very popular back in the early 90s. That was the heyday of chip making when there was a lot of money flowing out of National Science Foundation and into universities. And as a university student, you could take a class in VLSI design. You'd probably be using Magic to do the layout. You'd go ahead and get it fabricated through Moses on, say, an Orbit 1 micron process, get it back the next semester and test it. This happened all the time. Those are the heydays of VLSI, and there are a lot of us who went through that era who wish it would be like that again. And that tends to be the way I work, is trying to push back toward that kind of design. Obviously, in the modern era, there are a lot of ways you want to do things differently. So, and that's part of what is going on at Open Circuit Design and also at eFabless, which is the place that I'm now working. That was an opportunity I had to stop working at a company. I was working for Analog Devices. It was too much of a corporate atmosphere, wanted to get back into the startup. And this was a way to get the tools that I was working on up on a platform where they could be used by a community for doing open source development. So likewise, NetJen was developed by Massimo Savlati, who went on to be the Chief Technology Officer at Tanner Research, which was a EDA tool company that was eventually bought out by Mentor a few years ago. IRSIM was developed at Stanford about the same time I was there. XCircuit was developed by me, one of those scratch your itch kind of projects in which I needed a schematic editor. Sadly, there's never really been a good open source standard or any kind of standard at all for schematic entry, schematic capture. There was this one time somebody tried to make a set called EDIF, which was largely a disaster because you could do anything in EDIF and probably describe the architecture of my home in EDIF. Which is why it failed. It was too complicated for its own good. More recently, so when somewhere around 2005, 2004, I joined up with a startup company, the one that was eventually bought out by Analog Devices, called Multigig. And I was hired by them so that they could get cheap EDA tools to do their analog designs. But as we got into building real chips to do commercial, for commercial sales, to do real things, we found out that chips tend to need a lot of digital on them. They will need some kind of digital infrastructure. If nothing else, you want an SPI. Almost all analog chips right now will have some kind of SPI interface so that you can make the analog as freaking complicated as you want to. You just need to have a big register set where you set all their configuration bits, and you do all that when you power up. That meant we needed a digital flow. But we needed a digital flow that worked within the whole full chip design for a complete analog mixed signal design. So I was fortunate to have a colleague named Steve Beckew, who was from Caltech, and he had worked out this digital flow that used these old tools called SYS and VIS from Berkeley. And they sort of kind of worked. If you kept your Verilog very simple and had one clock domain and this and that and the other, it would work, sort of. So this is where, from the name BecQ, is where I get the name QFlow. That was started off as his flow. Eventually, I started replacing some of these old things like vis and sys with new and greatly improved things like EOSys. And for a while, I was using a commercial router that I got free use of because I helped the person who wrote it with some development work with Magic. So he gave me a free use license. So that kept me going for a while until I realized, well, hey, I have this flow. It's almost all open source, except it doesn't have a router. So I went off and wrote one. Likewise, I depend on a number of tools that are open source, but not specifically related to the stuff I do, such as EOSys. Gray Wolf, I've sort of taken over. That was a tool from Yale. The people who wrote it made it proprietary, founded a company off of it, are still running this. The version I use is the last open source version they had. And then XSpice, I should probably add iVerilog on there too, because I do make use of Icarus Verilog. So here's a little bit of recent development. I'm going to say that what I've described is basically end-to-end. You can figure out all the pieces that you need for that, right? It's placement, routing, static timing analysis, and generation of GDS. And a few other things in there, clock tree. All the things that are given to you, you take for granted when you're doing an FPGA. What about the clock tree? Well, the clock tree has been installed for you already. And then how about power up, power management, all that stuff? That's done. Those are blocks that are already in your chip, and you make use of them when you compile to a specific FPGA target. These are all things that have to be dealt with when you're doing a full chip design. I'll concentrate on just different bits and pieces of that flow and what I've been working on, whether they work, whether they work poorly or whether they work well. If they didn't work at all, it wouldn't be a flow. I wouldn't be talking about it. And the reason I'm only here now instead of maybe talking about it 2 years ago is the fact that it has been a sort of sketchily working flow for a long time. It's about now that I feel confident in saying it's at least close enough to a commercial tool set that I can say with some confidence that you can take a chip from Verilog and analog source end to end and get a chip GDS out of it and send it to a fabrication facility and get it made and at least have some good chance of it working when it comes back. So for digital routing, I have QRouter. It has, up till maybe earlier this year, been very slow, good for what we call small digital. That is, if you want to make little digital blocks that support the analog circuitry on a mixed signal design, say. You would have like, for an SAR ADC, you'd want a little digital block that does the digital control of your ADC. It was good for that. It was not good for microprocessor level design. It's based on, well, the original algorithm is what's called maze algorithm. It's a maze router algorithm, which you basically start at a source, figure out the cost of routing to any point in the design. You spread out over your entire design space until you find your destination, and then you backtrack over the lowest cost path. That's good for point-to-point routes. It scales very badly with size, and it's fairly poor. It does not give you an optimal route for a multi-node net. So the best thing I did for that was to create the idea of building a mask where you want the route to go. So I build out a trunk and branch system for a set of nodes and say follow that. This little shaded region shows that it's going to follow the innermost path as the ideal, and then as it fails to find that, it'll spread out until it finds something in this area. By restricting the amount of space you're looking for, you can find the routes very fast compared to having the entire space available to be searched. Also, all routing is done by a script. It's done in TickleTK. I was having a discussion about TickleTK earlier around lunchtime. But it's what I use for arcane reasons. Like synthesis, like EOSys, for instance, there's a standard script that will solve most of your problems. If you happen to have a particularly difficult routing problem, you could write your own script. It also has an interactive routing where you can just type those routing commands in at the command prompt and then watch it go through the different stages of routing. One of those embarrassing things which would keep me from coming to conferences and talking about this until this year is the fact that people would ask embarrassing questions like, do you do automatic power bus placement? And I'd have to say no. Well, I finally, realized, I have realized for a long time that that's something that you absolutely must have. If not for nothing else, you need to avoid IR drop in the center of a large microprocessor design, for instance. Also, you can't just go around telling people that after you finish doing all that routing, you need to wire up everything by hand. I thought it was a difficult problem. I ended up implementing it and found that all you really need to do is put posts at every power connection on the standard cells and then route one line straight through. And the router has absolutely no trouble, in most cases, just routing around those posts. So it turned out to be a much easier problem than I thought, so I should have solved it a long time ago. But anyway, it's there now. Another thing that this does that I'm pretty sure Yosis doesn't do, but Clifford is always surprising me with what Yosis does do. But clock tree insertion is a big problem when you're doing a full chip design like this. And this needs to be a combination of a solution in your placement as well as your routing. And if you have an FPGA core, it usually has an a clock H-tree structure already in place so that if you put in your clock at this point, it will evenly distribute it out to all the places. The hard part here that I had to solve in the placement tool was that the ideal way to solve it is to try to cluster all of your terminal points of your clock. And the only way, I had a sort of hacked way that didn't really work until I finally solved it in the placement algorithm to tell the placement tool that certain points in your circuit are permutable. So that, for instance, for the clock domain, you may have a whole tree of buffers, but the clock terminals A, B, C, D are exactly the same behaviorally as A, C, B, D. Everything in detail about that is timing. And at least for a first pass, the best timing you can get is if you cluster these things so that they're balanced. So by making the placement tool treat these as permutable, it will go down and find solutions in which everything is nicely clustered. So I went through one of this is a fairly small digital block, but it still shows you that, yeah, you have a clock. Once it's finished doing the placement, the clock is pretty centralized to the whole thing. The first set of buffers around the clock are clustered very nicely like this, and then that falls into 5 different clock domains in this case. One of those other embarrassing questions that just got solved last month is, can you do back annotation of routed parasitics into your static timing analysis? And the answer is yes, as of a few weeks ago. Was working with a person at the University of Texas who knew how to do the Elmore approximation, which is how you get delays, calculate an approximation of delay time from point to point from a set of resistance and capacitance. And so the one thing that QRouter knows how to do is walk the paths of the routes that it's created and tell you what is the resistance and capacitance at each point. And if you know how to calculate the Elmore approximation, then you can get a set of point-to-point delays, feed that back into the static analysis tool. Trying to make it ever simpler, I have finally gotten into making a GUI manager for the whole Q flow. So this is on efabless.com. There's no particular reason that I don't have it on Open Circuit Design other than the fact that my first cut at this is somewhat hard-coded to the directory structure that we have tech files on at eFabless. I'll eventually get it back onto Open Circuit Design. So it is open in the sense that if you go to the eFabless, you can actually find the source for this. It's not hidden away anywhere. But it's essentially one-button push end-to-end routing. Of course, every routing problem, or the whole synthesis flow problem, is going to have a set of parameters. But at least with a GUI like this, you can choose reasonable parameters. You can have somebody just go push buttons, 1, 2, 3, go down all the steps. At the end, if it fails at some point, then you can go back and see, all right, what parameters do I need to change? In the end, you can go then and figure out whether there are parameters that make it better. But it simplifies the whole process. Also, the fact that it's on eFabless is that we have a number of vendor processes that we use. So if you are using this on eFabless, then you don't have to worry about the part of setting up all the vendor tech files. Likewise, for LVS, one thing about open source tools, don't always trust them. Don't ever trust them. Always get verification. For the routing problem, it's always possible for a router to make a mistake. You want to know about it if it does, so you do LVS. One of the recent things I've done is at least try to make a nice GUI out of the LVS, so that's also a one-button push process. And assuming that the router is decently good, you have a good chance that it just runs through and says everything's correct. If not, you got to go send me a bug report, among other things. Usually it's something easy to fix. Last thing I fixed recently was that for the LVS process, NetGen, as I mentioned, it was written by Massimo Savlati, who went off to Tanner Research. And I had rewritten it so that it would do hierarchical LVS. It was almost like a professional tool. The one thing it was missing is it couldn't do parallel serial device combinations. So if you had a schematic where you drew one resistor, and then in your layout, you decided you wanted good matching properties, so you divided that into 20 resistors. It wouldn't be able to match them. It's not a hard problem. It's bookkeeping. It just takes a long time to write the code. So I've finally gotten done with that and can call NetGen a truly professional-grade tool. A few other minor things. In eFabless, if you're at tomorrow's talk about eFabless, I'll go over this thing called chiplicity, which is trying to simplify the whole process of chip design. But one of the things is to try to work with abstract views as much as possible. So I have written and debugged extra commands in the layout tool that will create abstract views out of straight layout. What am I doing on time? Here's some interesting things. All right, when you are simulating, when you're trying to verify a full chip, you would like to simulate the whole thing, analog and digital. That's a mixed signal simulation, or some people call it co-simulation, depending on how it's running. And it's a difficult problem. It usually kills your tools. In the FPGA world, one solution is you write models for all of your analog and say Verilog AMS, and then you compile everything as a Verilog model and simulate the whole thing that way. That's doable. A lot of that is abstracting a lot out of your circuit, and often when you do that, you're actually building your models of it separately from your actual physical design, so that you then need an extra step of verification to make sure you didn't screw up anything when you rebuilt it outside, right? You've got a pad frame in your physical design. In your iVerilog design, you've just got a core and you're feeding signals directly into the core. The pad frame has probably disappeared. Very easy to make a pad frame wiring mismatch. If you don't verify that, then your physical chip doesn't match your iVerilog simulation. Better if you can take your entire chip design, extract a netlist out of that and do a full simulation on that netlist. So in order not to kill the simulators doing that, these are the steps that we've been taking recently. One of them is there has been for a long time this feature called XSpice within NGSpice and Berkeley Spice. It was developed at Georgia Tech. And it's basically a digital co-simulator inside Spice. Its drawbacks are that it has fairly limited support. They had a few models that people made, and then beyond that, they stuffed it into the Spice source, and I haven't ever seen any more development on those models. They said, okay, oh yeah, you can just write your models in C. I don't know anybody who knows how to do that, really. I spent a bit of time learning. I just sort of barely learned how to do it, just enough to do this, which was useful. So I generated 2 new models for XSpice. Worked with Holger Volt to get them put into the NGSpice distribution. But it's a lookup table, so any standard cell you can model as a lookup table. Simply say for this combination of inputs, the output is this, and reduce that to a string. And this will cover 90% of a standard cell set. For the others, you may have a few things with 2 outputs. I created another one called genlet for a general lookup table, and then you can do multiple outputs that way, so you can catch the other few odd cases like full adders, half adders, and so forth. Latches and flip-flops, XSpice already had pretty good general purpose models, so I didn't need to reinvent the wheel there. But with these 2 additions, I now have a script in Qflow that will take any standard cell set, read the Liberty description file of that, find out what the function is of each standard cell, and map it to a XSpice function. So you can extract your entire digital core of your full chip into an XSpice model, and that part of it runs in Spice very fast. Not necessarily as fast as if you compiled an iVerilog, but it's still very fast. And if you've used Spice a lot, you will know that anything that has digital type sharp edges to it really kills Spice. It'll slow it down to a crawl. So anything that looks anything like digital, you would prefer to be doing in XSpice or something like that. The alternative is run all your Verilog stuff in Verilog as a co-simulator. So that is a communications problem, trying to run one process, iVerilog, Spice as a second process, and have them talking to each other, and talking to each other without getting lost. Fortunately, I found that problem was solved for me. I was poking around the web pages blog for XSpice and came across this one entry that said, oh, I have a co-simulator with iVerilog and XSpice, are you interested? And then Holger Vogt said, yes. And then there was nothing after that. So I finally tracked this guy down in Brazil. Fortunately, caught him just before his company shut down and he moved somewhere else. Otherwise, it would have been a complete loss. And he said, oh, sure, sent me all the code. So I finally worked between him, Holger, and me, got this put into XSpice. So there is a version of XSpice where this is compiled in, and it's fairly straightforward. And on the Spice side, you have an A model, which is what connects to XSpice. And you tell it you are running this model called DHDL. And you pass certain parameters to HDL. And whenever, actually what you do is you run the process from the iVerilog side. So the iVerilog has this new variable called DHDL sync. And that simply gives you the command line to run Spice. So iVerilog, then you compile this down into a module for iVerilog. And when it sees that, it starts up Spice and runs a communication pipe. And that takes care of the rest. There are a few caveats for it. It doesn't always work under all circumstances, but I found it very useful to run it in a way in which I take everything inside my chip. So all the digital there is synthesizable. That all corresponds to real physical stuff. It can all be compiled into XSpice. Outside the chip, you want to drive it with stimulus. That's not physical. There's not, so you can do all sorts of things with the Verilog that is non-synthesizable. You put that into an iVerilog block. And so this part of it is your stimulus, and XSpice is, and other regular analog Spice is the Spice side of that, and it all simulates relatively efficiently. So again, with a few caveats that sometimes you need to keep abstracting your analog models to make them run, I have been able to do full chip simulation in Spice with this. For sake of time, I'll just go to this. This is the one thing I'm interested in doing, which is just a step further from what I just described with the iVerilog co-simulator, and that is to develop an XSpice model that essentially takes the about VVP is the execution stage of iVerilog. You have a compiler stage, which gives you a sort of bytecode of instructions, and then VVP, which takes those instructions and run them. Is to take that code for VVP and compile that into an XSpice model so that when you run Spice, it will simply hit one of those, read in the VVP code, and then start running a instance of iVerilog, of VVP, inside XSpice. The trick here is ripping out the event queue from VVP and telling it to use XSpice's event queue. That way you don't have to worry about the synchronization between the iVerilog side and the Spice side. Everything that XSpice already knows about event synchronization is already there. You just make sure that all the things for each of your iVerilog processes goes into the same queue, and all the timing should be taken care of. That's my current pie in the sky project to work on as soon as I get around to having the time to do it. Although there are a few other wish list things. I would call that near-term development. It is definitely on my plan to do. There are a few other things that are wish list. One of them is that there is one last thing in the end-to-end flow, particularly if you're doing something microprocessor level, which is that you want RAM, and preferably you're going to do that with a RAM compiler. RAM compilers are typically proprietary and belong to the foundry. So the current state of affairs is that if you want RAM on your chip, you go to the foundry website, and they have some tool that will run. Would be nice to have an open source tool to do that. There is such a thing. It's called OpenRam. It's a project out of University of California at Santa Cruz. And it's all there. The main problem with it is it needs a lot of setup because you have to know how to design sense amps and all the other analog components of that so that it can then go put them together into a RAM block. The next thing would be to use QRouter for chip top-level routing, which is largely a matter of taking the masks that I was talking about in one of the first slides and changing them so that they can find channels between blocks on a chip so that you can do the full top-level routing. And that would also apply to the problem of routing to blocks that are not rectangular, which is something that QRouter, I wouldn't say QRouter doesn't know how to do it, but it does it badly right now. And then finally, I think Kunal probably covered this pretty well yesterday, but there is a definite wish list for being able to route something at the million gate level. Right now, all these tools just about uniformly die somewhere between 100,000 gates and 1 million gates. 100,000 gates is good enough to compile. It's plenty sufficient for the Pico RV32. I have done the ARM M0 and the ARM M3. And the ARM M3 is getting toward the limit, and anything higher than that, Kunal tried the Sci5, and everything stopped dead. So there is work there to be done, refactoring code and trying to make sure that it can do something of that size without killing all the resources. So that is what open circuit design is and where we're going with it in the near future. Are there any questions? So, yes, question. Microphone is coming.
So I got a question regarding the Vesta timing tool. You said it performs RC extraction. Does it do 3D parasitic extraction? Is it signal integrity aware?
Sorry,
does it do 3D parasitic extraction? Parasitic. And is it signal integrity aware?
No, it does not. Yes, so that would be another shortcoming that.
Okay, and how?
That pretty much limits you to processes that are above 90 nanometers, which on the whole, I think a lot of the other tools are going to start failing for other reasons when you get below 90 nanometers. For instance, QRouter just is not going to be able to know all the DRC rules that are prevalent when you get down, particularly right around 45 or so. You get all these optical design rules that are requiring you not to do certain run lengths. That's where the same sort of thing would come in for the parasitic extraction, and I think those are all going to have to be solved at the same time.
Okay, and does it generate a path so you can do back-annotated simulations?
Yes, yes it does. Yeah, that was the Elmore approximation was to create a file. I'm not sure if it's exactly SPEF format, but it's easy to get there if it isn't. Further questions? Yes.
Thank you so much for maintaining all these tools. Like, you're actually making it possible to use free tools to resolve issues, which is amazing. I know Tickle and Magic are like intertwined and one and the same, but can you add a Python front end to Magic?
Yes, it's true that Tickle came to be because largely John Osterhout, who wrote Tickle, is also the person who wrote Magic, and so much of the code was the same. It was trivially easy to rip out the core of the Magic command processing and replace it with Tickle. And once I knew how to do that, it was easy to apply that to other tools. Yes, I can do that with Python too. In fact, some of them do. I think Xcircuit and possibly even Magic have, you can compile the Python interface if you know how. There isn't much development on them though. The good news is I've been almost exclusively going over to Python since I started working for eFabless. So I've become an expert Python programmer in the last year. So things will drift that way. I can guarantee it. Yes, Clifford.
Regarding the co-simulation, the part that you described that you want to do, where you use Icarus Verilog from within XSpice. I was just wondering if Verilator wouldn't be better suited for this kind of thing.
Good question. That is something I'll talk to you about that. How about that? It may very well be.
Since we just had a talk on formal, I was wondering if if in your flow you have a lec tool, as you told us not to trust the placer and the router, but what about the synthesis tool?
Well, the synthesis is all done from Yosis, so I am largely depending on static timing analysis to do all the verification of everything. There are tools to do the verification of that before synthesis, or at least prior to all the back-end things that Qflow is doing. Beyond that, once you have the routed solution, static timing analysis is the best I have for doing that. I know there's more. There's also Kunal talked about this, a program called OpenTimer, which is, I'd say, vastly more capable than Vesta. And at some point, that will go into Qflow. I'd like Qflow to remain fairly flexible in being able to take one tool out and put another tool in. The main restriction is they have to talk standard formats. And right now, OpenTimer does not. So, but there should be some development on that, I think, that will make it more compatible. So that will help a lot.
Then I go.
Right,
Since you said kind of the full tool flow, just you got it working essentially a couple months ago, kind of the full stack essentially. Have there been any tape outs yet, or any plans, or kind of what type of first or coming tape outs do you expect from this tool flow?
Oh, numerous. In fact, one of the things I was planning to mention was that there are a number of other people besides the crazy ones that Steph mentioned who like to do the end-to-end flow with open source tools for a real production chip. One of them is NASA, because of the need to use processes that are either rad hard, or there's another company I work with in Arkansas called Ozark Technologies. They do high temperature or extreme environment chips, so they have to use special processes. They are also, because of the things they do, a single chip for a space mission or for some special purpose. It's very low volume. And so they're doing it through shuttle runs, and they often do not have the professional tools, the cadence seats and so on, to do this. So they want to do something fast, simple, and cheap. And so yes, so the Ozark I talked about, they have done a chip, verified, works. NASA Goddard, I have a person who used Qflow to do one that's now scheduled to go on 3 space missions.
What kind of nodes are you talking about in those chips?
180, I think, on both. And there was a question over here.
I was just going to say if you needed some earlier help, I'd love to be part of it.
Okay, all right.
It's not really a question.
I will take that into consideration.
So really fantastic work. It's really great. I love it. What about test insertion, test routing, and pattern generation?
Yes, DFT is, yeah, still one of the embarrassing questions that I have to answer no for yet. but it is, it's on the longer to-do list. But yeah, generally speaking, all the design for test stuff, the JTAG chains and so forth, is fairly, again, like the, like a lot of the other things I was doing, it's not hard. It's just a lot of bookkeeping, so it's a lot of coding to do, and I will do it when I have time to do it. Sorry? Maybe. I'll have to check that out. Okay. All right. Next speaker. All right,